All right, everyone, settle in. Pull up your chairs, adjust your lumbar support, grab your coffee, your yerba mate, your Earl Grey, whatever keeps those synapses firing. We are back in the chair.
Back in the virtual IDE. I've got the mechanical keyboard warmed up. I can feel the tactile bumps already. It's a good day to write some code.
It really is. The screen is glowing. Dark mode, obviously. We aren't savages. And looking at the monitor, we're right back where we left off in the last session. I see the cursor blinking right below our previous work.
That's right. And just to orient ourselves, because context is everything in systems programming, let's just take a quick glance at what's already on the screen.
Yep, lines 1 through 5.
We have the F32 struct definition we hammered out. Pub struct F32, a simple tuple struct.
Right. And sitting right on top of it, that whole list of derived traits, clone, copy, partial leak, partial lord, and of course debug. It's sitting there looking pretty. It's a nice little container. But honestly,
Yeah.
it's a bit of a ghost town right now. It doesn't actually do anything yet.
It's inert matter. It's like a car chassis on blocks with no engine. We've defined the shape of the data. We've said this thing holds a 32-bit float, but we haven't defined any of the rules. We haven't said how the universe is allowed to interact with it.
We have the noun, but we're completely missing the verbs.
Exactly. We have the data type, but we lack the behavior. And today, the mission is very, very specific. We are going to breathe some life into this thing. We are going to write its implementation block.
The impl block.
The impl block. And to start, we are going to be laser focused on one single, absolutely critical function. The constructor.
The entry point.
The front door. The source material we have in front of us calls for a public function named new.
New. Simple. Classic.
Yep.
Love it. But before we start typing, and I know, the keyboard is right there. You want to write code. I have to play devil's advocate for a second.
Please do.
Because I look at that struct, F32, and I think, why all the ceremony? Why do we need a special function just to make one of these? Why can't I just type let my number if 32 10.0 and just be done with it? Why do we need a constructor at all?
That is, without a doubt, the fundamental question. And you're right, if we were just writing a simple wrapper to, rename a float for clarity, you wouldn't need this. We wouldn't be having this conversation.
But we're not.
We are not. Remember the title of the source material we're working from? Robust Floating Point Utilities.
Robust. That's the key word, isn't it?
That's everything. Robustness implies safety. It implies guarantees. If you look at a raw F32 in Rust or C or C++ or pretty much any language, it's a bit of a wild animal.
Yeah.
It has to adhere to the IEE 7fit4 standard.
Which is a beast of a standard. Most people don't realize what's in there.
Oh, it's a whole world. It means your float can be a nice, respectable number like 3.14, but it can also be infinity. It can be negative infinity. And most dangerously for us, for what we're trying to build, it can be NaN.
Not a number.
The dreaded NaN. The ghost in the machine.
It really is. It's the value that isn't equal to itself.
Exactly. NaN breaks everything. NaN is not equal to itself. If you try to sort a list of numbers and just one of them is NaN, your whole sort logic completely falls apart because NaN defies the laws of total ordering.
Like a logical black hole.
It is. So our F32 struct isn't just a wrapper, it's a contract. It's a promise to anyone who uses it. We want to be able to promise that if you are holding an instance of F32 in your hand, it is guaranteed not to be NaN.
Ah, I see. So if I could just manually construct it, like F32, F32.NaN, then I've broken the promise on line 1. I've smuggled a bomb into the supposedly safe building.
Precisely. You violated the invariant.
Invariant. Okay, that's a CS term. Break it down.
It's a fancy term for a simple idea. A rule that must always be true no matter what. For our answer at the club door, checking IDs. And that bouncer is the function we are about to write. Pub FN new.
I love that image, the bouncer. Sorry, pal, you're a NaN. You're not on the list.
Yeah.
Okay, I'm sold. We absolutely need a gatekeeper. Let's look at the blueprint the source gave us. It says, infl F32 pub FN new F32 option.
That's our roadmap for the day.
Okay, my hands are on the keyboard. Let's do this. I'm starting with the container for this behavior. I'm typing impl F32 and an opening curly brace.
And just stop right there for a second. Let's just savor that curly brace.
You want to savor the syntax. You're a true enthusiast.
I want to savor the architectural decision it represents. In some languages, like Java or C++ WetM, you define the methods right inside the class definition, all mixed in with the fields.
Yeah, it's all one big block.
Right, but Rust makes this clean separation. We define the data up there, and now, completely separately, we are defining the implementation down here.
It feels like keeping your ingredients on one side of the kitchen and your recipe book on the other until you're ready to actually cook.
It is. But it also enables something called local reasoning. When we are inside this impl block, we have special privileges. We're on the inside. We can see and touch the private data inside F32. But as soon as we close this block with that final curly brace, the rest of the world is locked out again. This block is the only place where the raw data is exposed.
It's the sterile lab.
Yeah.
Got it. Okay, we're inside the block. Tab indented, of course. Now we need to declare this bouncer function. The source says pub.s new. So I'm typing pub space, SSN space, .new.
Okay, let's unpack that pub keyword.
Visibility, I mean, that's pretty standard stuff, right?
It is standard, but it's absolutely crucial here. If we just wrote snew, this function would be private by default. It would only be usable inside the specific module we are writing.
Which would be pointless.
Totally pointless. This is a utility library. We want other people, other modules, maybe even other crates entirely to be able to create an F32.
Right. And here's the kicker. This connects back to my first question.
Yeah.
If this constructor function is private, and the field inside the struct is also private, which it is because we defined it as F32, without putting pub on the inner float, then literally nobody, nowhere can ever make one of these.
Exactly. It would be a hermetically sealed box, a completely useless type. By making this one function pub, we are cutting a very specific, very controlled window in the wall. We are saying this is the only authorized way to create this type.
It's really powerful when you think about it that way. Okay, so pub. Now, new, it's funny looking at that word. In my old Java and C# days, new was a key word, a special thing the compiler understood. New object.
Right.
Here, I'm just typing it like any other function name.
And that's a very distinct Rustism. In Rust, new is not special to the compiler at all. It's just a function. We could have named this function create, make, construct, or even Shazam.
Shazam, val F32. Kind of like it.
It has flair, I'll give you that. But it's terrible for readability. The Rust community has collectively, and very wisely, agreed that if you have a primary common way to create a type, you call it new.
It just reduces cognitive load.
Massively. When I pick up your library for the first time, I don't have to hunt through your documentation to find the make it button. I just instinctively try type name.new.
It's like door handles.
Right.
They could be shaped like, I don't know, pretzels or something, but we all generally agree on how a door handle should look and work so we don't get trapped in room.
Exactly. Convention over configuration. It's a beautiful thing. So, pub, fn, now we open the parentheses.
The parameters, the inputs, what we're taking from the outside world, the source says val F32. Okay,
New.
typing that in now. Val : F32.
And here is where the drama begins.
Drama. It's just a variable declaration. Val is an F32.
It's the antagonist of our little story here. That val is an F32. That means val comes from the outside world. It is untrusted. It is raw. It's the Wild West.
I see what you mean. This val is what the user wants to turn into our safe, sanitized F32. But we have no idea where it's been.
We don't. The user could be passing us 1.0, right? They could be passing us -500.23. Fine. They could be passing us F32.infinity, which is also fine for our purposes.
Yeah.
Or they could be passing us F32.nn.
The poison.
The poison. At this exact moment, inside those parentheses, val is Schrodinger's cat. It could be a perfectly valid number, or it could be the thing that brings our whole system down.
And the entire purpose of this function, our bouncer, is to open the box and look at the cat before we let it in.
Correct. We are accepting the raw material. This is the transition point. There's a brilliant computer scientist, Alexis King, who has this great phrase for it. Parse, don't validate.
Parse, don't validate.
Yeah.
Okay, what does that mean in this context?
Well, a lot of the time, people take in some data, they check if it's good, that's the validate part, and then they just keep passing the same raw data around. But here, we're doing something better. We are taking raw data, F32, we're checking it, and if it's good, we are turning it into a completely different type, F32.
We're parsing it into a new, safer representation.
Exactly. And once we have that F32, we never have to check for NaN again. The type system itself proves that it's valid for the rest of its life.
So we're front-loading all the safety checks into this one moment of creation.
We are at baking the safety into the type itself. It's a much more robust way to build software.
I love that. Okay, so we've accepted the risk. We have our potentially dangerous val. Now we need to tell the world what we're giving back. The return type. The source is very specific here. It doesn't say test F32, it says F option.
And this is probably the most critical design decision in this entire snippet of code.
I'm typing it out now. the little arrow F day, then option, and inside the angle brackets, F32.
Let's just pause and really stare at that. Option. Why? Why not something else?
Well, it goes back to your poison analogy, right? If the user gives us NaN, we can't give them back a valid F32. We have to refuse. It's against our invariant. So we need a way to say, nope, sorry, I failed.
Right. Now, in other languages, or even in other REST contexts, we have a few choices for how to signal failure. Let's call it choice A, panic.
Yeah, the nuclear option. Just crash the program. If valid is NaN,
Yeah.
panic. No NaNs allowed, buddy.
You could absolutely do that. It would certainly prevent the NaN from ever existing inside an F32. But is it robust?
Not really. If I'm writing a server or a video game engine or a flight control system, I definitely don't want the whole thing to come crashing down just because one weird calculation produced a NaN that I try to wrap. That's the opposite of robust.
Exactly. Panicking is for unrecoverable, catastrophic errors, things that indicate a bug in the program, something that should never happen if the code is correct. But receiving a NaN in a math-heavy application, that's a predictable, albeit undesirable, occurrence. It shouldn't kill the entire process, so panic is out.
Okay, that makes sense. So choice B. We could return a result. Something like, it's off to 32, my error enum.
A very strong contender. Result is fantastic when you need to provide detailed information about why something failed. You could return error, NaN error.value was NaN.
But in this specific case, is there any other possible reason it would fail?
Nope. There is exactly one failure mode we are concerned with here. The input value is NaN. That's it.
So the error type would be kind of redundant. If you get an error, you already know exactly why. You don't need more information. It just adds noise.
It's overkill. It's like using a sledgehammer to crack a nut. Which brings us to choice C.
The option.
The option. It is the most elegant, minimal way to signal success or absence. It's
Yeah.
binary. You either get some at F32, meaning here is your valid number, or you get NaN, meaning sorry, couldn't do it.
It's honest. The function is just saying, look, I might not be able to do this, and you need to be prepared for that.
And crucially, it forces the caller, the user of our code, to listen. Think about C programming for a second. In C, if a function fails, it might return NUL, but NUL is just a pointer to address 0. It's just a number. If you forget to write an if, PTR, NULL, check, and you try to dereference it.
Boom. Segmentation fault. The infamous billion-dollar mistake.
Exactly. But in Rust, option isn't NUL, it's not just a value. Option is a type wrapper, an enum. You literally cannot get to the F32 that might be inside without handling the option first. You have to unwrap it or match on it or use an iflet.
So the compiler itself physically prevents the user from ignoring the possibility of failure.
It does. The return type becomes a form of mandatory documentation. Just by reading the signature option, I know as a user, oh, this operation is fallible, it might not work. I don't need to read a single line of comments. The type signature tells the whole truth.
That is just beautiful. It's self-documenting code at its finest. Okay, so the signature is locked in, pub, fnu, F32, option. I'm typing the opening brace for the function body now. We are officially in the logic.
We are in the belly of the beast. Time to make the donuts.
The cursor is blinking. We have val. We need to inspect it. We need to check its ID.
Right. The source material implies we are filtering for NaN. So we need to ask val a question.
I'm starting an if statement, if val, and there's a method for this, right?
There is. Built right into the primitive F32 type.
Is not.
That's the one. If val.isNone.
How does that actually work? I mean, under the hood, how does the computer know a particular pattern of bits is NaN?
It checks the bit pattern directly. In the IE 754 standard, a float is defined by a sign bit, a block of exponent bits, and a block of mantissa bits. A NaN is a very specific, weird case where all the exponent bits are set to 1, and the mantissa is something other than 0.
So it's just a bitmask check, basically.
Pretty much. The CPU has a specific, highly optimized instruction to check for this state. It's incredibly fast.
But it's not a performance concern.
Not at all. It's a few cycles. Negligible.
Okay, so if val dot is NaN, I'll add the curly braces. Now, what do we do if it is NaN? This is the moment of rejection.
We have to fulfill the contract of our return type. We promised we would return an option. If we have a failure, what is the option variant for failure?
None.
None.
So inside the if block, I'm just typing.
None.
That's it. Simple as that. It implies, I have nothing for you. The operation failed.
The bouncer just points to the door. Not tonight, pal.
Your ID is fake. Get out. Okay, closing brace for the if. Now for the other case. The else.
the happy path. The sun is shining, the number is valid. It's a 7.5. It's a negative pi. It's a real usable number.
Right. Now we need to actually create the thing. We are finally using the struct definition we looked at 10 minutes ago. We're going to wrap the value.
We are, but we can't just return the F32 itself.
No, because the return type is option. So we have to wrap it in the success variant, which is sum. So I'm typing sum.
Correct. The value has to be inside sum.
Okay, so sum F32.
Yeah.
Let's just look at those parentheses for a second. If sum opens a parent, then F32 opens another parent, then val. Then we close the F32 parent. Then we close the sum parent.
It's a hug inside a hug.
A hug inside a hug. I like that.
The inner hug is F32. That is the tuple struct constructor itself. That is us physically placing the now verified F32 data into the F32 slot. And this is only allowed here because we are inside the impl block. We're inside the sterile lab where F32 is defined. Even though that inner field is private to the outside world, we can see it. We have the keys.
So we wrap our safe val in F32. Now we have a value of type F32. Then we take that whole thing and wrap it in sum. Now we have a value of type option.
And that matches our function's return signature perfectly.
And that's the whole function. I'm typing the closing brace for the else and then the final closing brace for the function new.
That's it. Let's stop typing for a moment and just look at the code block we've written on the screen. It's short. It's what, 5-6 lines of logic? It's surprisingly simple.
Yeah, it feels almost too simple for how much we've talked about it.
But complexity isn't measured in lines of code. It's measured in implications. Think about what this little block of code has achieved. Before this function existed, we had a struct F32 that was just an empty shell. Now, by creating this single public entry point, we have established a rigid, unbreakable boundary. And because this is the only way to make an F32, we have effectively proven a theorem about our program.
Theorem. That sounds a little grand.
It's true. The theorem is, for all instances X of type F32 that could possibly exist in this program, the value inside X is not NaN.
That's the invariant. We've enforced it.
I've enforced it with the full power of the type system. And because of that invariant, we can now trust the traits we derived last session. Remember partial ic.
Yeah.
The default implementation of partial ic for raw float says that NaN L using, which is confusing and leads to bugs. But since we now know for a fact that we don't have NaNs in our type, our F32 behaves like a good mathematical citizen. It behaves more like an integer. X is now always true for our type.
It's the concrete foundation. If the foundation is cracked, if we let just one NaN slip in here, the whole house of logic we build on top of it falls down.
Right. If we just blindly wrote some F32's val without the if check, we've lied to the compiler and to our users. And in systems programming, lying is the absolute worst sin.
Okay, I'm looking at this code and I'm feeling really good about it. But I'm trying to put myself in the shoes of the user now, you know? I've imported this cool new library. I want to actually use it.
Okay, let's simulate the user's code. Let's go to main.rs in our minds.
Right. So somewhere in my main function, I want a number. I type let -m equals f32.new 10.5. Looks good.
Stop. What is the type of that variable, -m?
Well, I want it to be f32, but looking at our signature, it's not. It's option.
Right. -m is an option. You can't add it to another number yet. You can't print it directly as a number. It's a box that might contain our number.
So the user has to deal with the box. They're forced to. They'd probably write something like if let send, if let 32.new 10.5.
Exactly. A classic REST pattern. If I was able to successfully create this number, then give me access to it, call it n, and I'll use it inside this block.
Or if they are feeling daring and they know that 10.5 is a valid number, which come on it is, they might just reach in and grab it with let -m equals f32.new 10.5.unwrap.
The unwrap hammer. I, the programmer, promise this works, and if I'm wrong, you have my permission to crash the program. And you know what? That's perfectly fine for hard-coded constants like 10.5. But if that value was coming from, say, user input or a network sensor,
you'd want to be more careful. You use something like let -m equals f32.nusensorito.expect, critical sensor failure.
Exactly. This API design forces the user to consciously make that decision. Do I crash if this is bad? Do I use a default value instead? Do I log an error and retry? We, the library authors, didn't make that decision for them. We just gave them the necessary information. This operation might return none.
It's empowering the user rather than babying them, or worse, surprising them with a crash they didn't expect. It feels like very respectful API design.
It is. It's all about clarity and handling errors explicitly.
So, quick question about the copy trait we derived last time. How does that play into this?
Oh, that's a great question. Because F32 is copy, when we return some F32 val, we aren't doing any complex memory allocation on the heap. We're not dealing with pointers or anything slow. This is all happening on the stack.
So it's just a bitwise copy of 4 bytes.
Exactly. It's dirt cheap. Calling F32.new 1.0 is effectively instantaneous. We're talking nanoseconds. It's just a check and a copy.
And that's so important. That answers the inevitable, why not just use raw floats? Objection from the performance nuts. It's too slow to add a check.
It's almost never too slow. And you know it is slow. Spending a week trying to debug a weird graphical glitch that only happens 3 hours into a game session because a NaN propagated through 50 different systems and finally caused a matrix inversion to fail.
Oof. Yeah, I've been there.
That is expensive. Checking it at the door is cheap. An ounce of prevention is worth a pound of cure.
Or in our world, a cycle of CPU time is worth a week of debugging.
Huh. I'm putting that on a t-shirt. A cycle of CPU time is worth a week of debugging. That's the absolute truth.
Okay, let's do a quick recap of what we've built in this session. We started with a raw, defenseless struct. We talked about the dangers lurking in the F32, specifically the NaN monster.
We established the need for this constructor pattern, a gatekeeper. Even though Rust doesn't have a formal constructor keyword,
We implemented pub NaN. We made it pub so the world can actually use it. We took in a raw, untrusted val.
we very deliberately chose option as our return type to signal fallibility without crashing the program.
We wrote the core gatekeeper logic,
Yep.
if val.is now.
No. Some F32.
And we discussed how this one tiny function upholds the entire robust promise of the library. It is the sole guardian of our invariant.
You know, it really makes me think about all the other places in code where we let things slide.
How do you mean?
Like, how many times do we pass a string around, we assume is a valid email address, but we never actually checked it properly at the boundary? Or we have an integer that represents a user's age, but we never checked if it's negative. All the time. It's called stringly typed programming, and it's a huge source of bugs.
Right, and this pattern making a new struct, keeping the insides private and forcing a check in the constructor, it applies to way more than just floating point numbers.
It absolutely does. It's the parse don't validate philosophy in action.
So instead of passing a raw string around and having every function check, is this an email, over and over again?
You check it once when you try to create an email address struct. And if it succeeds, you now have a value of type email address. From that point on, any function in your system that takes an email address as an argument knows, without checking that it's dealing with a validly formatted email.
That's exactly what we just did here. We check for NaN once inside new. Now any other function that takes an F32 as an argument can just do its math worry-free. It doesn't need to constantly recheck for NaN.
We front-loaded the complexity to make the rest of the entire system simpler and safer.
That is a seriously powerful takeaway. The code itself is simple, but the philosophy behind it is really deep.
That's the best kind of coding, isn't it?
It really is. Well, looking at my screen, the cursor is blinking at the end of that final closing brace on the impl block. I think our work here is done for today.
The code compiles in my head. And usually that means it'll compile on the screen.
Usually.
Yeah.
Let's not jinx it. But yeah, the logic is solid, the syntax looks right. We have a robust entry point for our floating point utility.
The gatekeeper is on duty.
And no NaNs are getting into this club.
Not on our watch.
All right. Code looks good. It compiles.
See you in the next compile.